Okay, so in this movie clip, we are going to study the details on transient response of PN junction diode. So transient response indicates that we are going to switch. We are going to turn on the PN junction diode, or we are going to turn off the PN junction diode. However, think about the original state before turning the diode off. What was the state of the PN junction diode? Definitely it should be on, right? So from on to off, or from off to on. How does PN diode work while its state becomes switched from on to off or from off to on? So that part can be understood with the help of transient response of PN diode. Okay, so let's do that in this class. Okay, guess I need to switch my color. Right. So suppose that now the APN junction diode is under forward bias. Okay, and then suddenly the diode has been turned off at time of 0. Okay, can you see that the PN diode is completely turned off at time t of 0 second? This time t, and here 0 and current of diode. So your diode is now applied to a forward bias. Okay, but let me write down it again. No, like this. Okay, so at time t of 0, the switch has been opened. Then this diode should be turned off completely. No current is flowing throughout the PN diode. That's true. But my question is, right at the moment when the switch is opened, can the diode flow current? Yes or no? Yeah, the answer should be yes, because at t is 0 minus, before the switch is opened, this DC bias can deliver its own power toward the diode. Then this diode should be forward biased so that it is flowing a certain amount of forward biased current. So that current would make what? Yeah, that original forward biased current should form this excess hole concentration in the N side, as well as excess electron concentration in the P side. So this stored excess carriers would be the root cause for the diode to be still flowing a tiny amount of current, even though it is fully switched off, because this mechanical switch is completely off, but still a tiny amount of current is flowing. Why is that? Because of these stored excess carriers. Okay, so in some sense we can explain, or we can understand the physics in the process of transient response in PN diode. Under forward bias, a sufficient amount of excess carriers has been well kept in the quasi-neutral regions on both sides, P side and N side quasi-neutral regions. And suppose that at time t of 0, the switch has been turned off, switch has been opened, so that no voltage has been applied across the PN junction diode. However, ideally, the diode should not flow any current at all. However, because of the stored excess carriers, the PN junction diode is still flowing its own current. So it requires it is necessary, certain time duration, to remove all the stored access carriers throughout the PN diode. Then we can claim that this PN diode is fully reverse biased or fully turned off. Okay, so these stored access carriers, why these access carriers are stored in these quasi-neutral regions? We can say that because of the diffusion capacitance component. Okay, so this diffusion capacitance, C sub D, because of it, the voltage across PN junction depletion region cannot be instantaneously modified. Okay, so that is the main physics and why the diode cannot be turned off abruptly and suddenly. Okay, so again, on the left hand side, you can see that the delay, the switching delay time from on to off, I mean the between on and off switching delay time, is due primarily to the time required to change the amount of access minority carriers stored in the quasi-neutral regions. Okay, so that is the main reason, and as we have learned, you may simply and easily catch up what I had said. Okay, so now let's do more deep analysis how to turn off the PN junction diode and what would be happened while the diode is turning off. So as described in this lecture note, in order to turn the diode off, the access minority carriers in quasi-neutral regions must be removed completely. Then we can claim that this diode is off. So how to remove those stored access minority carriers in quasi-neutral regions? Yes, we should flow a certain amount of current flow. I mean, the stored access carriers should be moved out. So the movement of access minority carriers itself would provoke a certain amount of current. So by flowing a net carrier flow out of the quasi-neutral regions, then we can claim that the access minority carriers which is stored in the quasi-neutral region must be out, must be completely removed. But is it the only way to remove all the stored access carriers in the quasi-neutral regions by flowing the net carrier flow? Not really. There is another way. In the quasi-neutral regions, there are a sea of majority carriers. So suppose that, for example, from the P side, the hole has been injected into the N side quasi-neutral region. So now the injected holes becomes, works as a minority carriers. However, in the N side quasi-neutrals, there are humongous amount of majority carriers, which is electron. So those majority carriers, electrons, can easily would tend to recombine with injected holes from P side. So recombination event would be another way to remove all the stored access carriers in the N side quasi-neutral region. So that way is the second approach, how to fully turn off the diode. Okay, so in summary, there are two approaches to remove the stored access carriers in PN diode. Number one, you can just you should force a certain amount of carrier flow out of the quasi-neutral region, or even end the recombination event to be happened in the quasi-neutral regions. Okay, so theoretically that sounds okay, but how to verify those two approaches? I mean, how to experimentally demonstrate the p-n junction diode has been turned off from on state toward the off state by net carrier flow or by recombination or both. How to monitor it? How to verify? So people has come up with a switching circuitry. Okay, so this switching circuitry has been drawn on the left hand side. See here. So here is a PN junction diode is given and connected to the two different circuit branch, A and B, I was saying. 4 biased circuitry reverse biased circuitry. So at time t of 0, so I mean the t is uh, before time t of 0, the VF and RF, these are VF are connected into the PN junction diode, so that we can claim that the PN junction diode is on when time t is less than 0. However, when at the time of 0, the switch has been moved from A node to B node, so that VR and RR are connected into the PN diode. But take a look at the polarity of this battery power supply, plus minus, so that uh, this PN junction diode is now reverse biased when time t of 0. So at t is equal or higher, the PN diode should be off ideally because it is reverse biased. But the question is, when the diode is becoming turned off, the excess carriers are fully removed when right at the time of 0, right? So this event, this physical event should not be happened in real. Why? At least a certain amount of time is necessary for the access carriers stored in the quasi-neutral region to be moving, right? So that using this switching circuitry, we can limit how much current can flow throughout the PN junction diode. Then we can monitor how much current has been flown throughout the PN diode, and at some point, at a certain time, uh, after the T of 0, then the diode is really turned off. I mean, the PN diode is in the end has been reverse biased. So we would like to see the switching process, switching steps from on to off using this switching circuitry. So let me explain more details how this switching circuitry is doing for PN diode. So at time t is less than 0, the forward current is flowing. This is approximately VF over RF. Okay, so what kind of voltage value and which register I have used, you can define your own forward bias current. So this current is flowing throughout the PN diode. So excess holes and excess electrons are well stored in both quasi-neutral regions. And now, when the switch has been moved to the node B, the reverse bias has been applied. And this current flow should be very limited by this resistor. Okay, so this minus IR, that means the current direction is opposite, so that minus VR over R sub R. So this value would limit the total amount of current in this circuit loop. Okay, so this value should be well chosen. Otherwise, it is hard to see and hard to control the reverse bias current throughout the PN diode. But the problem is, even though not because of the excess stored excess carriers, this PN diode is still forward bias. Forward bias means this PN diode is kind of short, right? So right at this time and more, maybe from here to here, still excess holes and electrons are moving toward in this direction. Electron has been moving in this direction, hole is moving in this direction. So it is kind of a conducting material, right? At this time duration, okay. But this is a kind of shorted out. However, because of this resistor, the current is flowing in this direction. So the role of diode is kind of metallic wire, and this RR is the only thing that blocks the current flow in this circuit loop. Okay, so that is the main reason why minus IR has been flowing for a while. So when for what time? Yeah, for from 0 to TS. Okay, so this TS is going to be defined as storage delay time. Okay, this would be used as a figure of merit to evaluate the transient response performance of PN diode. Anyhow, so from 0 to TS, the minus IR is the only limiter uh, for current flow in this loop. That means this diode is still forward biased. In other words, this diode is a kind of a metallic wire because it is still forward biased. Why? Because of the stored access carriers. They are still moving throughout the PN diode. They're still flowing the current. That is the main reason why the PN diode is still working as a conductor. Then after TS, now all the stored access carriers are fully removed so that this diode is kind of, this diode is really actually a reverse biased, as we have learned in ideal diode theory. So the current flow in this direction from N to P direction should be very limited to the minus I naught. That is a saturation current of PN diode. Okay, so minus IR is maybe here. That is should be very small amount of current. So in the end, the current flowing throughout current flowing in this loop should be very limited to the minus I naught. This is a saturation current throughout the PN junction diode. So now the stored excess electrons and holes are removed. So in the end, the current value should be asymptotically approaching to the saturation current for the PN diode. So now this RR is nothing. I mean the effective resistance value of this diode is much higher than the RR value. Okay, so whole current throughout this loop is fully governed by this effective resistance of diode. Okay, so this time duration has been defined as a reverse time, recovery time. Okay, and this TRR, which is the summation of storage delay time plus recovery time, is defined as reverse recovery time. Okay, so TRR, TR, TS, those are the main figure of merits in evaluating the performance of the transient response of PN diode. Okay, but usually the storage delay time is the main one. How come we are not using T sub R as a figure of merit? Why is that? If you have a chance to read out all the sentences, the book said the TR cannot be used as a figure of merit for PN junction diode because of stray capacitance coming from measurement systems, cable or measurement system itself, unwanted and unidentified capacitance component would affect significantly this TRR and TR. So this part would be very dependent of the measurement system. So people don't want to be, confused with the measurement system that each person is using. So people are using this storage delay time as a, kind of standard figure of merit in evaluating the performance of transient response of PN diode. Okay, so in that sense, a certain equation to define storage delay time TS is necessary. So maybe in the upcoming slide, I'm going to show you the full derivation steps, how to get the equation for TS, storage delay time. So before moving forward, let me clarify again and let's review how the stored access carriers are removed out. So suppose that let's take into account a P plus N diode. So one side is the PN junction diode, so that many holes would be injected into the N and less amount of electron would be injected into the P plus side. So this flow would be the main one in determining the forward biased current level. Okay. In other words, the Q sub P, the total amount of stored charge in the inside quasi-neutral region with holes, injected holes, is way higher than the total amount of charge obtained and implemented by the injected electrons from N to P plus side. Okay, so QP is much, much higher than Q sub N, this P plus N diode under forward bias. Okay, so now let me draw and imagine the excess hole concentration in the N side as a function of X. As we have learned, this delta P sub N of X should be like that. But at time t of 0 means when 0 or less, the diode is forward biased, so many excess holes are stored and keeping this profile of excess hole concentration when time t is 0 or less. However, when time t is higher than 0, the switching circuitry, this guy, this switch has been moved to the node B so that this PN diode has been reverse biased so that from that time, the excess holes are now moving toward where? Yes, in this direction. Okay, so all the stored holes are moving from N to P side. That is main reason why this plus minus bias has been applied, and many. Oops. Yeah, at time. Come on. What happened to my pen? Let me see. Okay, now it's working. So when time t is 0 or less, then switch has been moved to the node B so that the PN diode is kind of reverse biased, but still the stored holes on the N side would move toward the N side. In other words, the stored excess holes would be moved from N to P side. So the current is flowing from N to P. But since the total amount of access holes are much sufficient, is too much stored holes are available in the N-side quasi-neutral region, so that once you apply a plus voltage onto the N-side, many holes are ready to move toward the N-side. That is the main reason why we can treat this PN diode as kind of short circuit. Okay, so here the stored holes are now moving toward the P side. Then, if you think about how the excess hole concentration in the N side profile, well, in the end, all this part should be moved out. So as time increases, many holes are now moved, is now moving toward the P side, okay? But here, notice that the slope, all the slope are identical. Why is that? Because a DC bias has been applied. Let's take a look at here. DC VR has been applied across PN diode so that the whole remove of the whole removement is, the rate of removing holes out of the inside quasi-neutral region is constant. So that is the reason why I can draw and write down the equation for P sub n as a function of x. Okay, so this I is a current flow uh, throughout in this direction. Okay, all right. Let me see. Then let's make a note. Okay, so take a look at the two figures on the right hand side. So here, uh, this time t of 0 is the moment when the switch is switched from node A to B. I mean, the PN diode has been reverse biased at the time t of 0. So this current level is IF, and this current level is minus IR. Okay, and that is a TS. But if I draw how the voltage has been applied across the PN diode, well, definitely when time t is less than 0, the forward bias has been well applied. However, at this storage delay time, all the forward bias voltage across PN diode has been gone. And in the end, it's going to be negatively biased. In other words, PN diode is really actually reverse biased. So that is the main reason why we are using a storage delay time as a good indicator how good or how bad the diode can be turned on and off. So here is the example that I have taken from the example problem set in your textbook. So qualitatively, we may understand it. Uh, Go back to this switching circuitry and remember it. So bring it into, let's use it for solving these problem sets. So what if we are increasing the forward current, IF? How this measured curve can be modified? Yeah, there is IF has been increased, so you can see that this plot, right? And switched open since the minus IR has not been modified, so same, but you should determine storage delay time, it becomes longer or shorter. Increase IF. So more holes and more electrons are injected into the other side. So I mean the amount of stored access carriers are increased. That means the more electrons and holes should be removed to become off, right? So storage delay time has been more elapsed, it becomes more longer, and then it's going to be turned off, okay? All right. What about this? Increase IR. So that means IF is same, but you would like to increase IR. So suppose that this IR minus IR has been increased, then TS becomes short or long. For the same amount of excess electrons and holes stored in the quasi-neutral region, you're gonna flow much higher current from N to P, so that the total amount of holes and electrons stored in the quasi-neutral regions are leaked out at a rapid pace, so that TS value should becomes shorter. So you will see this curve, okay? All right, so this storage delay time is very dependent of a minus IR. And the last one is what if we are decreasing the minority carrier's lifetime? So lifetime indicates how long the minority carriers can survive in the sea of majority carriers. So if we decrease this minority carrier lifetime, the recombination event in the quasi-neutral regions would be more activated or more strong, so that for the given IF and minus IR, the storage delay time becomes shorter, so you will see this curve. Okay, so qualitatively, we may understand how the stored excess carriers are removed out of the PN junction diode. That is a key idea in understanding the transient response of PN diode. So now is a good timing to derive the whole all the detailed process. No. We should build up the equation for the storage delay time. So as I have told you, the TS has been used for a while. The primary figure of merit used to characterize the transient response of PN junction diode. So using what was the name? Charge control model, I guess. Let me double check. Where's my note? Yeah. Anyhow, charge control model in P plus N diode. So all the holes stored in the N side, that was denoted as Q sub P. So dQp dt is determined by how much current is flowing and how much recombination event has been happened. And since now we are talking about the transient response from on to off, this current becomes a minus IR, reverse current. So just plug in the minus IR into I, and you're gonna get this equation. And now, this equation is valid when the time is between 0 to Ts. Why is that? Because in this time interval, the charge, the excess holes stored in the quasi-neutral regions are removed out. So now we can solve this first order differential equation. So by separating the variables, dt is moving here, and all this term has been moved on the left hand side, and then you can do integration work. Then let's do that. This 1 IR plus QP over tau P dQp is equal to minus 1 dt integration, right? And then time is 0 to Ts, okay? And here Qp when time t is 0, and this Qp is when time t is Ts. So you can solve this integration. So here ln IL plus ln what's IR. No way. Oops. I guess my pen is not working. Anyhow, you can solve this integration equation, then you're gonna end up with this Ts is equal to tau p lifetime times ln 1 plus IF over IR. So please do that by yourself. I guess that's a very easy job. If not, please ask me or ask a TA, then he or I can help you. So please do that. That's a very simple integration work. So that's all for today's lecture. And I guess in lecture number 20, you can see that some PN junction, some summary of important PN diode concept and some its applications of PN diode. So I'm going to explain it after midterm exam. Okay, maybe. I guess maybe in the next movie clip, I'm going to explain you the PN diode applications, light emitting diode, blah blah photodiode and others. And yeah, that's all the contents that I'm going to explain in the next upcoming movie clip. So please review what I have taught you on PN junction diode, and that's all for the PN diode. Thanks for your attention, and see you in the next movie clip. Bye bye.